All right, in this video, we're going to look at more related rates examples, especially like the word problem type related rate problems. All right, so in doing related rates, remember that time is the input that causes the change. So every variable needs a chain rule, which means you're going to get a lot of things that look like dxdt, dadt, all this different stuff. All right, time is the change that's causing other changes. All right, so that's what we need. All right, so first example, all right, ship A is traveling due west toward a lighthouse. All right, so let's put our lighthouse. Now we have a ship going west towards it at 15 kilometers per hour. All right, ship B is traveling north away from the lighthouse. So ship B is going north at 10. All right, find the distance between the two ships when ship A is 4 kilometers from the lighthouse and ship B is 3 kilometers from the lighthouse. All right, so we're trying to find the distance between the two ships when ship A is 4 kilometers away and ship B is 3 kilometers away. All right, so by drawing a picture, I can already see that this is a right triangle problem. All right, we have the distance we're trying to find. Let's call it, I don't know, d for distance. We know that d squared is 3 squared plus 4 squared, which is 9 plus 16, which is 25, which is plus or minus 5 when you take the square roots, but remember, negative distance doesn't make sense in this scenario, so they're 5 kilometers apart at this time. All right, and this will end up being useful in the actual related rate problem, which is find the rate of change between the two ships at that same time. So if we quickly just redraw this picture. All right, lighthouse, boat 1 going this way, boat 2 going this way, and we're going to figure out how is this distance here changing. Well, if we want to know how this distance is changing, we kind of just saw what we need. We need to know how far this boat is away and how far this boat is away. And we know that d squared equals, a squared plus b squared. All right, the Pythagorean theorem always gives me the distance of these two, or between these two ships. And now again, I don't want to plug in values right now, because that would kind of force ship A to always be the same distance away from the lighthouse, right? The distance is changing, so I can't plug in things until after I take my derivatives. All right, so now I take the derivative of this equation. I get 2d dd dt. Maybe I shouldn't have called it d, but it's fine. dd dt. 2a dA dt plus 2b dB dt. Okay. And now we just plug in everything that we know. All right, d represents the actual distance between them at this time. All right, that's just one snapshot in time. The distance between them we just found is 5. All right, dd dt represents how the distance d is changing, which is actually what we're trying to find, so we don't know this yet. All right, a is the distance of A from the lighthouse at this exact time, which that is the 4. And the a dt is how the side of this triangle is changing, and we're going towards the lighthouse, which is making a smaller, so it's going to be negative 15. All right, b is the exact distance we are at this exact snapshot in time, that's going to be 3. And dB dt is how is this side b of my triangle changing. And since b is getting farther away, b is getting bigger, and that's going to be positive 10. All right, so now we just kind of simplify a bit. 2 times 4 times 15 is negative 120 plus 60. All right, so our final answer is at this exact snapshot in time, all right, the rate between them is changing at negative 6 kilometers per hour. So you could say it's decreasing by positive 6, or the rate is negative 6. All right, so basically the ships are actually getting closer together at this exact time because the distance between them is decreasing. But you can see the what we did. We start with the Pythagorean theorem because that gives us the distance between these ships. We take derivatives, so now we're talking about the rates of all the changes. Then we can start plugging in the stuff we know. And it's normally just one thing we don't know. And if we solve for that one thing we don't know, that's how that quantity is changing. here we have a cube. It's being filled up with water. At a rate of 10 cubic inches per minute. If each side of the cube is 5 inches, what side do I have that? That's it. Is 5 inches. How fast is the depth of the water changing? So we're kind of looking at the water part there. And we want to know how is the height of that water changing. All right, so we need to create some equation that has to do with the height of the water. And I think what we're going to have to do whenever you're filling something with water, it's always going to change the volume. So the volume of the water part is 5 times 5 times h. All right, so that's the water part. Now if I take derivatives, all right, this is 25h, so I'm going to take its derivative, get 25, and then h is dh dt. All right, how is the volume changing? How's the volume of this blue bit changing? Well, I'm pouring more water in, so that volume is 10. I'm putting that amount of water into, it's going to change the volume and increase it. And dh dt I don't know yet, but by dividing, I can figure out dh dt. So now I know the change in the height per time is 2 over 5, and then we use the same units, cubic, or sorry, it's not cubic, it's because it's a single thing, inches per minute. All right, so 2/5 inches per minute is how the height of the water is going to be changing. All right, so this one is the same scenario as the first one, but slightly different question. All right, we still have our boats. All right, we have our distances away. Oops, we'll call this A and this B. But this question is, how fast is the angle from the lighthouse to ship A to ship, from the lighthouse to ship A to ship, I think this should be a B here, ship B. So we're talking about basically saying this angle here. What color have I not used yet? All right, this angle here. All right, we're trying to figure out how that angle changes as A gets closer and B gets further away. All right, so the first thing we do is figure out some equation that relates all these kind of quantities together. All right, something that gives us this angle, and we have the opposite and adjacent sides, so it's going to be tangent. So the tangent of theta equals b over a. And now we can find the derivative of this equation. So derivative of tangent is secant squared. And then we have to do the chain rule to take the derivative of theta. That's d theta dt. And then through b over a, we're going to have to do the quotient rule. So we're going to do low d high minus high d low over low, the original bottom squared. All right, so that's just all derivative rules. Now we plug in what we know. So what do we know? We know a and b because they're telling us a is 4 and b is 3. All right, so I can put in a 4 here and a 3 here and 4 squared there. We know how b is changing from the same way we know before. This ship is going farther away from the lighthouse, so b is increasing by how fast the ship's going. A, the change in A, this side of this triangle is getting smaller because A is going towards the lighthouse, so it's going to be negative 15. Right. D theta dt, the change in the angle is what we're trying to find. And we just need to know secant squared of theta. Well, secant squared of theta is 1 over cosine squared of theta. And cosine is ca adjacent over hypotenuse. Right. And in this angle, or this triangle, the adjacent side is A, well, it just happens to be A, that's funny, is 4. And the hypotenuse we figured out before, this distance is 5. All right, so we get secant squared is 25 over 16. now it's just a bunch of simplifying. 25 over 16 d theta dt is 40 plus 45 over 16. The 16s are going to cancel. And d theta dt is 85 over 25, which those are all divisible by 5. So it's the 85 divided by 5, 17 over 5. And then we're talking about an angle, so it's going to be radians is the unit for an angle per hour, because that's the time unit we're using. All right, so really seems really complicated. I mean, it is a little complicated, but we basically create an equation that uses our value we're trying to find. Really, all you can do for this angle is use trig. So we have our equation that uses the angle we're trying to find the change in, take derivatives, and just plug in all the stuff you know. And sometimes you have to do a little bit of extra work to the side. It's not like given to you in the problem, but like to figure out this hypotenuse we had to do for the Pythagorean theorem one. We had to do Pythagorean theorem to figure out that. All right, here we had to do some SOHCAHTOA stuff to figure out secant squared of theta. All right, but either way, you take derivatives, remembering those dt's all over the place, and then solve for the one thing you're trying to find. So really the hardest part is really these like first two steps, making your equation, taking derivatives. From there, it's just plugging in a lot of things. All right, so quick summary. As with all problems, drawing a picture is going to help. You'll be able to see like where the quantities are going. You'll instantly be able to see if it's a right triangle problem, because half of these are right triangle problems. Again, only plug in a value at the start if it's not changing throughout the entire scenario. For pretty much all the scenarios we looked at, like in the triangle, if you plugged in like 3 at the beginning, it would force us to always be 3, but since it's changing, you don't want to plug it until after. And just remember your derivative rules, like the last example we saw we had to do derivative tangent, and we also had to do the quotient rule. All right, so just remember all those things, and really it's just going to come with practice. You're not going to understand it right after this video, but as we do more practice, hopefully you can kind of see where these things are coming from.